So let's continue. We still are in the theme of why Shipyard Nuclear, and our next speaker is Eric Ingersoll, founder and managing director at LucidCatalyst and TerraPraxis. Please welcome.
Well, I hope everybody's was really woken up and stimulated by that last talk. It's pretty exciting. So what I'm going to do is the study that Kirsty presented called the Missing Link Study was a kind of vision of how we could really address the decarbonization of fuels, not as a substitute for electrification, but as a complement to electrification. So if you think about sort of decarbonization from two ends of the system, you can decarbonize on the supply side, the way fuels are made, and begin to sort of distribute those through the system. And you can decarbonize on the demand side, the way the fuels are used, which is substitution by electrification. Unless you're very, very optimistic, you have to realize that it's unlikely that we will be able to finish the electrification approach in the time that we have. So the idea of decarbonizing the fuels is not to slow us down on electrification, but it's so that all the other things that we're having a hard time electrifying can also become zero carbon. So that study was really designed to kind of advance that broad story and broad thesis. And it was read by the Electric Power Research Institute, and they said, we would like to hire you to do a much more detailed study of the techno-economics of the kinds of production systems that you talk about in the Missing Link report. So the EPRI-study that's referred to here is that study, and at the end of the presentation there's a link to that, but you can also find it if you search around on the LucidCatalyst website. So what I'm going to do today is just take you through the costing methodology that we use to arrive at an estimate for this production platform. So this is slightly less than 400 meters long, this ship here. The small ship is just a fuel transport ship that's picking up ammonia. It's about 70 meters wide. It's about 30 meters tall, produces 1.2 million tons per year of ammonia, has a somewhere between 20 and 30-year economic life on station before having to go back to the dry dock for maintenance, and it has a 90% capacity factor. And as Rowley mentioned, it's making ammonia for less than $300 a metric ton. So the methodology we used was first to define the target. So in this case, the kind of largest ammonia, largest typical ammonia plant is about 1.2 million tons per year. So we decided to base it off of kind of what's called a world scale ammonia plant. So then we developed kind of the main systems and subsystems for the cost estimation. And those created what we called the cost categories. We then identified the cost precedents or proxies for each cost category. So what is the data source we'll use for estimating that? And is there something that is exactly like that, or do we have to somehow interpolate from another data set? And then we scale the precedents or the proxies to the appropriate scale. If the production facility that we're modeling is bigger or smaller, then we have to make sure that we are scaling correctly the precedent, and then bring all the costs from the references to present currency, and then develop an operating cost model. So this was our breakdown of the main systems and the other systems needed for the plant. So there's a power island making electricity, which is feeding electricity to high temperature electrolysis. There's an air separation plant, And the air separation plant is a standard commercial cryogenic air separation plant extracting ammonia from the atmosphere, nitrogen from the atmosphere. There's a desalination system to provide water for the electrolysis plant. And then there's cranes and a hull to fit it in. And there's other kind of fit out stuff like moorings and some ammonia storage tanks under in the hull, and there's crew quarters and so forth. So that's the kind of main breakdown. And then, for the power island, there's reactors and the secondary loops. There's steam generators. There's water treatment for the steam system. There's the power block, which has the turbines, the turbine foundation, feed water system, condenser, and related systems. And then there's the switchgear. So this is then how we think about the kind of transformation of the data that we're finding for these different systems into the cost model. So we need to really examine for example, if we're looking at an ammonia plant, it's probably built on land. We don't need land for our ammonia plant, so we have to find the factors that are related to the land cost and remove them from the estimate. In some cases, there's a difference in the delivery model. So if it's an EPC delivery as opposed to a build-to-own, owner-built plant, there may be EPC fees in there. So we need to make sure that the kind of delivery model and the situation that the data is coming from is adjusted and is relevant to the estimate that we're trying to make. We also have to look at what kind of basis is the costs. Is it based on estimates by another analyst? Is it based on quotes from vendors? Or is it a real project where money was actually spent and what they actually ended up spending? So it's also very helpful to understand the extent of design completion in the precedents. So for example, if we're looking at an engineering study, was it a very complete design that they costed, or was it just a kind of preliminary design? And then also it's very important to look at the conditions. So things like labor costs, manufacturing costs, materials costs, what kind of, was it a first of a kind project or kind of a routine project, et cetera. And then finally to make sure that we're comparing an asset with a comparable lifetime. So that's kind of the hard work in making a cost estimate like this. So then I'm going to take you very quickly through the precedents that we found that we were able to use for coming up with this estimate. So obviously there's commercial ammonia production, and there's new approaches to all-electric ammonia production, represented by the ThyssenKrupp illustration. There's existing natural gas extraction and processing and liquefaction ships. And so we have two examples there. And then we have actually a very detailed study done by Thorcon for a shipyard manufactured nuclear plant. So we use that as the kind of power island for the ship. And then there's a number of very detailed studies by the Idaho National Lab in the United States on nuclear-driven ammonia plants. So there's a picture of a 380-meter floating LNG extraction and liquefaction platform. It's basically a floating refinery for natural gas, much more complicated than what we're doing. And this shows kind of how they're designing these ships into modules. So the different kind of slices of the ship are doing different functions, and those modules can be made onshore, all in parallel, and then assembled very quickly using the very large cranes that are available in a shipyard. This dramatically increases the productivity and decreases the construction time. This is the Thorcon design. This is kind of a very early picture of their design, but I'm going to show you some more pictures to show that there was actually a fairly complete design basis for the estimates that we used here. So they completed a drawing package and then received estimates from a shipyard in Korea, and we were under NDA, and we were able to use those estimates for our project. The thing that I would mention here is that although it seems kind of more far out than a traditional SMR project or proposal, actually, in most cases, the estimates that you get for SMR construction, and this is something that we are quite expert in, the estimates are not done with a complete design. So if you go to an existing SMR vendor and say, how much will it cost to build a plant, they can't show you a completed drawing package for the whole plant. And part of the reason for that is that generally the nuclear vendor does not do all the drawings. The EPC does the drawings. And so if they don't have an actual project that they're building, they won't have an EPC, and the EPC will not have done the design, and therefore they can't give you an accurate estimate. In this case, they did have a full drawing package, and they were getting the estimate from a shipyard, and the people who did the design had designed and built 8 ships before in the same shipyard. So we're talking about here a team where the engineering and design group and the manufacturing group are both very experienced at working together, and we're actually getting an estimate from the kind of delivery partner who's going to deliver the project. So we think this is actually one of the better estimates for advanced reactor costs that we've seen. So very briefly, just to show you kind of the status of the design, here's the power island. On the right, we have the reactors, in the middle of the turbine, and on the left, the switchgear. Sorry, the contrast is so bad. This is actually a very nice picture, but this gives you a sense of the scale. That's meters at the bottom. They had, this shows that they had sort of all the equipment spec'd out for the supporting systems for the turbine, the feed water pumps, the condenser system, the cooling, backup cooling systems, and so forth. Here's the steam generation cell. This is just showing kind of structural details, like they've actually spec'd out the structure that's required to hold these things, and some more detail on the turbine-related equipment, but you can see that the pony turbines to spin the turbine up and everything, it's all there. And this is the switchgear. Unfortunately, the contrast is so bad you can't see this, but maybe you can download the presentation later. This is the heat island where the reactors are. It's got all the components and the structure and so forth. And here's just another view of that, showing the decay heat removal system. And finally, this is the reactor, which Thorcon calls the can. And so it has a kind of a. How many people know about molten salt reactors in here? Should I explain some of this, or? Okay, I'll just do a very quick explanation. So one of the things that's different about molten salt reactors is that the fuel, the uranium, is dissolved into the salt that is in the reactor, and this the reaction heats the salt. The nuclear reaction heats the salt up, and the salt is then pumped through a heat exchanger to another loop, and that loop then is heat exchanging to make the steam, and but the nuclear reactor, the pot here, is called a pot because it's really different from a normal nuclear reactor in that there's no pressure inside the reactor. So it's really kind of a, modest. It's like a bucket, a pot with salt in it. So it's not very expensive. It doesn't have to deal with pressure conditions. It just has to be able to contain a hot salt. So this whole can here, their business model is that this is an operating expense. Okay, so this is not part of the CapEx. This is like the fuel that you would buy for a light water reactor, this whole piece of kit here. And so I'll tell you how much that adds to the cost in a moment. So anyway, this would all be made in this kind of highly efficient production system. And again, we had very detailed numbers on different high temperature reactor technologies driving electrolysis and ammonia production from very detailed Idaho National Lab studies. And so here it is all integrated together. So first, to talk a little bit about the reactor, because this is something that probably people are like, well, why are they doing it that way? So the replacement, you can operate molten salt reactors for many years, but there is currently some question about what the corrosion rates would be. And so most of the people commercializing molten salt reactors have assumed that you would need to replace the reactor less than every 5 years. So in this case, they're using a 4-year replacement rate. By the way, they're all speccing materials that should last 20 years or something. So we're not actually at some danger level here. It's just that commercially, it's safer right now to predict a replacement in 4 years. So when you look at the way the costs are being amortized, they assumed that making the can would cost a certain amount, and then they multiplied the labor cost for the can by a factor of 20 to come up with a conservative estimate. So this is a kind of a wild overestimate, in my opinion, of what the can is likely to cost, and it adds, right now, if you amortize it over 4 years, it adds $3.70 per megawatt hour to the cost. So not very much. The salt is 34 cents per megawatt hour. The fuel, the uranium, is $5.13 per megawatt hour. The staff is about $4 a megawatt hour. And the rest of these things are, sort of necessary but not very expensive. So your OpEx is $14.40 a megawatt hour, or 1.4 cents a kilowatt hour. And when Rowley and Kirsty were reviewing the deck for me this morning, they said, "Are you sure the decimal point is in the right place there?" And it is. So the amortized CapEx for the power plant, the rest of the power plant, the hull and all the other stuff, is about another $10 per megawatt hour. So that's about $24 or $25 a megawatt hour for that plant. And then here's the CapEx estimate. So I'm not going to read all these numbers off to you guys, but what I will say is that, so the darker the green, the more kind of confidence we have in the estimate. So obviously for the air separation, ammonia synthesis, piping and controls and so forth, these are all things based on real commercial plants and estimates that were based on those plants. So there's very good sort of basis for those estimates. The high temperature electrolysis, although it's not commercially available today, that is, there were 4 major engineering studies over the course of about 12 years in the United States, one after another, so revising and improving the estimates. And the last one included a full design for the system, vendor quotes for every single component, and quotes from vendors for supplying the solid oxide membranes for the electrolyzers. So although that looks like that's $298 a kilowatt for those of you, or a little bit less than that, that seems low compared to what people are quoting today. Most of the quotations that we've looked at for high temperature electrolysis are actually for very small systems. And when you start looking at much larger systems, you can achieve much lower costs quite quickly. Then on the power plant, actually, although it sounds kind of, probably to most people, it sounds outlandishly cheap, most of the power plant that we are basing this estimate on is not complicated nuclear stuff. It's stuff that you can get from commercial vendors. So the heat exchangers and the steam generation, there's a commercial quote from a supplier, and they supply heat exchangers commercially. And they understood what was needed, and they delivered a quote. The steam plant, the steam turbine and pumps and the feed water heating system and the condenser, very standard stuff, for a very good firm quote from a vendor. The electrical systems, very good quote, and we reviewed this with the comparable electrical systems for other power plants of the same size, and this was actually higher than those. So we think this is a very, very good number. There is a little bit of, in the other equipment, there are some things that, you might have slight variances on, but nothing that would really impact the overall kind of accuracy. The hull and the reinforcing, the design was actually shown to several certification agencies, and they made some recommendations about the strength for the hull, and those recommendations were added to the quote. And then there's installation, and the installation quote is obviously, we made that light green instead of dark green because it's this hasn't been done before, and we may have kind of significant variations on what those costs would be depending on the installation conditions. But again, that's a very small part of the cost, so we don't see that really impacting the overall cost. So the surprising thing here is that most of the system is very straightforward and is either something that the shipyards have built before or something that's very close to what they've built before. The only thing that isn't really is the reactor can, and that's part of OpEx, so it doesn't affect this, and it already has a big kind of error margin built into the estimate that we used. So we actually, the surprising thing here was really how little uncertainty there is here. That, I think, was a surprise. It was a surprise to us, and it was also a surprise to our clients at EPRI. So this is just a levelized cost analysis. I'm not going to go over this, but you can see this if you download the EPRI report. And we did identify. So I guess another question is, how conservative were these estimates compared to? So this was not meant to be a first of a kind estimate, but it is. But for many of the projects that we were basing costs on, it's not clear that they were really nth of a kind. So the ammonia plants, although they're commercial technology, they're not built in a way like they would be in a shipyard. And same with the electrolysis plant and other things. So when Kirsty and Rowley were showing that kind of declining cost curve, and there was a sort of mass production bar out there that was very small, we see a lot of opportunity for mass production to lower the costs of these things, which are, even though they're commercially available today. For example, in China, a large turbine for a coal-fired power plant costs $80 a kilowatt, and in the United States, it costs $300 a kilowatt. And part of that is difference in cost, labor costs, but the main part is that they have mass production for those turbines in China. They make 50 or 60 a year in one factory instead of 2 per year, and that makes a big difference. So we see, in general, we see a lot of opportunity for that kind of reduction, but there's also ways to combine systems and to benefit. So for example, you need nitrogen sweep gas for the electrolysis plant, and you're making nitrogen from the air separation plant. So you can reduce costs by combining those systems and optimizing. The way the Haber-Bosch plant is designed is really designed from a conventional Haber-Bosch plant for making ammonia. There are things you can do if you're using electric-based system to optimize that and reduce cost further. So there's a whole bunch of those things. We also don't model really very much energy recovery from the Haber-Bosch loop. And that may be enough to provide all the steam for the high temperature electrolysis, for example. So there's a lot of opportunities for costs. And, compared to a land-based plant, when you reduce the cost, you get to make your ship smaller or you get to increase the production from your ship. And this gives you sort of an additional benefit in terms of another reason to reduce costs, because you get to reduce that kind of CapEx as well. So that's it. That's how we came up with those costs. And if you're having trouble sleeping, download the report and you can read all the details.
Thank you, Eric.